Okay, this will be a video about parametric equations and vector calculus a little bit, and this will actually be divided into several videos for this section, and you have just one packet of notes for that, and then we'll do another section, and that will cover everything that we have. So these are equations that you should have worked with in physics, and it's just where we have x and y are normal sort of equations, but we also have t or we have theta. And we will definitely deal with ones with theta in it after we're done with these sections with polar coordinates, and they'll have thetas. So basically this third parameter variable, the t, we call the parameter. Okay, so the third thing in there we call the parameter. And so then we call equations parametric equation. So what these equations do is we're trying to graph, so say this example 1, we want to make a table and try to graph this function. Well, the difference here is you're going to end up with a graph that looks kind of familiar when we're done, but we're graphing it where this parameter is only defined from -2 to 3. So we have a beginning and an end point. Now you can think of t, most of the time when you deal with these problems, t is time. So you can think of it like we have something moving, some kind of particle moving or in the plane, and it's moving in the x direction and it's moving in the y direction, so it's making a curve instead of straight line motion. And it's moving with respect to time. So the time controls it. Maybe sometimes it's going faster and sometimes it's going slower and it's going at different speeds. And so we will naturally lead this right into finding instantaneous rates of change at certain specific points to find out how fast it's moving and in each direction. So right now we just want to talk about what it kind of looks like if we make a sketch here. So we're going to make a table. Well, this time in your table, you're not just going to have x and y, we're going to have t. So we're going to make 3 columns here, and we're going to have time, and we're going to have x, and we're going to have y. And then when we graph it, we're going to actually put arrows to show the direction. So we have more here now than just the curve. We actually have a direction that it's following. Now we can plug in anything we want, so we might as well pick things that are nice. So I'm going to start with I'm just going to use the integers that we cover here. So t equals -2 is the smallest value in our range, in our domain there for t. And if t is -2 and we plug that into x, we would get -2 squared, which is 4, minus 4, which is 0. Then we're going to take the -2 and we're going to plug it into y. So we take the -2 and plug it right there for t, -2 over 2, -1. And then we're just going to keep doing that for some values. And again, I'm going to pick nice values that are easy for me to graph. So I'm going to pick t is -1. So I plug -1 in for x. So into this t, that's where I'm plugging in. So -1 squared is 1. 1 minus 4, -3. And then I plug -1 into y, and I'll get -1/2. And so let's do one more, and then I'm going to plot those points, and then I'll just keep adding to that. So let's say we have t is 0. Well, if t is 0, x is -4, and y is 0. So let's go ahead and start trying to make a little bit of a graph here. So my first point there is at t equals -2. So my starting point, x is 0. And y is -1. And you can even think of this like an ordered pair here. That's what I'm graphing. So I'm graphing 0, -1. So here at -1, I want to put a point at 0, -1. And then my next point is -3, -1/2. So let's count off some points here. So -3, -1/2. About right here we put a point. And then -4, 0, we have a point. So we're going to connect these with a curve. And then I'm also going to add an arrow because I have a direction there. So I'm going that direction because that's the order that it goes when time goes from -2 to 3. So let's do another point. So if time is, or t is 1, which we can think of as time, it doesn't have to be time. but we're going to get negative 3 and positive 1/2. So we'll go over here and plot that. Negative 3, positive 1/2 is right there. So we're going to come around here. Oh, come around this way through this point. The board isn't oriented very well there. And then we're going to get 0. If we plug in t equals 2, we're going to get 0, 1. So our next point is at 0, 1. So we're coming right through here. And I'm going to put an arrow so I know we're going that way. And then if time is 3, which is the end of our graph, we're going to get 5 and 3/2. So we can put a solid dot there when I get to that point. 1, 2, 3, 4, 5, and then we're at 1.5. So right about there. So we're coming around to here. And then we stop right there. So we can put another arrow if we want. And so this is the graph that we get. And that would be the entire graph. Now you can graph this on the calculator also, and I'll do that here in just a minute. So let me get the calculator started opening. But so that was one thing, and we indicated direction by putting the arrows on there. And then the next thing says, let's eliminate the parameter. So we're going to do that. We're going to eliminate the parameter before we graph it on the calculator so that we can see the sort of rectangular equation that we get, so that we can look at it and see what we think that we should be getting here. And as soon as the calculator thing gets out of the way, you can look at the graph and see that it kind of looks like what the graph might be is a parabola on its side. So let me get this out of the way here. All right, so if you look at it carefully, you can see that it does look kind of like a parabola on its side. My graph is really yucky but because of this big fat pen, but it does look a bit like a parabola turned sideways. So let's see if that makes any sense with what we do when we eliminate the parameter. So what we do to eliminate it is we do exactly that. We just eliminate it. So here were my equations. X equals t squared minus 4 and y equals t over 2. So I want to get rid of t. So I want to have just x and y. So I have a regular equation that I'm used to. So the easiest one would be over here to solve for t by multiplying by 2. So I get that t equals 2y. Now I'm going to take that and substitute it in for t. So x equals 2y whole thing squared minus 4. So x equals 4y squared minus 4. Well, if you remember from Algebra 2, this is definitely a parabola opening to the right. And the way you can remember that is if it had said y equals 4x squared minus 4, you would recognize that as a parabola that opens up, that goes down to -4 for the vertex, and then this 4 makes it skinnier. Well, when you switch the around and you switch x and y, all that does is move it, it turns it so it opens to the right. Right is equivalent to up, and then it went left 4 instead of down 4. And if you look at this graph, it appears to do exactly that. You can see that it looks like it opens to the right. It looks like a parabola that opens to the right, that's skinnier than normal and has been moved down 4. So if we were to graph the whole thing, that parabola would actually look like that, and it would continue on, where my parameter stops my graph here and here. So I've got a beginning and end. So for my parametric equation, I just have a piece of that parabola. So if we wanted our parabola to be the same graph, then I would have to restrict the domain here. So this is my equation, but now I have to say, okay, wait, but I can't have everything there. I can only have certain x values. Well, if you look at that, we can figure out the x values that I need. The original problem had t going from -2, so we know we started at -2. Well, if you plug that in to into your parametric equations, then we would find that we would need to restrict the domain from, if you take it and put it into x, you put -2 in there, you would see that you're at 0. So it means x would be going from 0, and then t is 3. So my last number there would be x would be 5. So that means I would have to say, yes, I can have that, but it has to be restricted where x is in the interval 0 to 5. But actually, since this equation actually has y for the kind of like acting like the independent variable, we need that restrictions for y. So that's even easier. Just plug in -2 to this equation, and you're going to get -1, and then you plug in 3, and you're going to get 3/2. So we would say it has to go from, we would want that equation to have those restrictions, that y has to be between -1 and 3/2. And so then that would give us the same equation if we restrict everything. So we got to kind of cut it off. Now, on your notes paper, there's 2 statements there that say, what do you notice about the graphs of these other things? Well, so what we're going to do is we're going to graph them on this calculator, and we're going to compare them to, we're going to compare them to the graph that we just made a second ago. So let me get this to not open up like that. Okay, so let's look at the graph that's there. So we're going to type these in. So I'll show you how to enter a parametric graph. So you add a graph page, and you should be sure you're doing this with me with your calculator. And when I'm on the graph page, I want to do a parametric graph. So I go to menu, and I go to number 3, graph entry edit. And under that, I can choose function, equation, parametric, polar, scatter plot, etc., etc. Well, I want parametric, so I pick number 3. Now here it's going to give you x and y, x sub t and of t and y of t. And then it has something to do about steps and things. So we'll talk about that in just a second. So let's go ahead and type in the first one that says x equals 4t squared minus 4. And go ahead and use t here. A lot of times I use x for everything, but here we have to use t because that's the parameter. If I can get it to push. There we go. 4t squared minus 4, and then we want to enter y, and y is t. So y just equals t. Now down here we have the interval from 0 to 6.28, and the reason that's there is because a lot of times we're graphing polar equations, which we'll talk about later, and that's basically 0 to 2 pi. But here we want to go from -1, it says, from -1 to 1.5. So we just go over and change that to -1 to 1.5. Be sure you just pause the video if you're trying to enter everything. And then t-step. Well, what t-step means is how many values, what it's going to count by to basically make a table and plot those points. So 0.13 is fine. If you make it teeny, 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 tiny, like 0.00000001, it may take forever to graph. So don't do that. Just 0.13 is fine, or you can even just do 0.1. And then hit enter, and it graphs it, and there we go. And if we look at it, if I move this equation out of the way, you can see that you get the same graph that we just did. But we have a different equation, 4t squared minus 4 for x and t for y. All right, so let's do another one then. So let's go ahead and open another page, another graph page, and let's choose parametric. Also, we could have just entered another graph on the same page. Matter of fact, let's do that. So I'm going to go back so that you can see that. It'll plot in another color. So I just hit tab, and it will default to another parametric equation. So let me go ahead and enter that one, and it is 4. Remember, when you have parentheses, to be sure you say times, parentheses, 2 sine t plus 1, and then we need to close that parenthesis, and then we need to write parenthesis again and square that because we want to square, so be sure your squared is in the right place, minus 4, and then for y we want 2 sine t and then plus 1 outside of the parentheses, so watch all your parentheses there. and we want to go from the values that it tells us. So it's again kind of defaulting to that 0 and 6.28, but this is going to go from negative 1.571, and if you're not familiar with your trig or your basically your pi overs as your kind of decimals, that's basically just pi over 2 or negative pi over 2, and then it's tells us to step up to 0.253, and then just go ahead and let it count by 0.13s, and you get another graph. And let me see if I typed it right. 4 times, oh nope, I didn't type it right. So I thought it was supposed to look the same, so I need to click on that and I need to fix that. So I'm just going to hit tab and arrow up, and if you can see what I did, that +1 right there is not supposed to be in that parenthesis. So I need to get rid of that and close the parenthesis here. It was supposed to be sine of t, so 2 sine of t plus 1, then whole thing squared minus 4. So hopefully you caught that when you did it. If not, fix it just like I did. Just hit pause and fix it. And now we see it ends up basically right on top of the other one. And you can barely see it, but you can tell the difference, okay? So there's lots and lots of ways. The point of this is there are, you know, essentially infinitely many ways to represent the same thing using parameters. And notice that the 3 of those all looked very, very, very different as far as the equations went, but they all, in fact, produce the same graph. All right, so then here's an important concept here. So we want to fill in the blanks here. When you have rectangular equations on restricted intervals, it shows the path. So we see the path that something's traveling. Parametric equations show the path, but they also show the direction, and those are the arrows that we draw, and they can also show the speed. Now, on the older calculators, you could see the speed a little better because they graphed really slowly, and so you could see it kind of tracing that out, and you could see the speed of it. This one graphs it so quickly that you really can't see that, but it can show you the speed if you follow it. All right, so I'm not going to do example 2. I would suggest strongly that you graph example 2 on the calculator, making sure you figure out what domain to graph that on, and then I want you to see what it looks like and see what you think about it. But we're going to go ahead and go to example 3. So go ahead and turn the page to example 3. We're going to do the same thing we just did for these 2 equations. So we're going to make a table. So we're going to put t, and then we'll have x, and we'll have y. Same thing, but we got the parameter t here. Now, since we're doing trig functions, then obviously the choices that we want to pick for t are going to be things that we know in the unit circle, things that we can actually answer and deal with. So we'll start with 0 will be fine because it doesn't tell us anywhere to start or stop this. So I can start or stop it anywhere I want, and then we'll see if we need to deal with that in a minute. So I'm going to start at 0. And so then I'm going to plug 0 in. So if I plug 0 in for x, cosine of 0 is 1. So I get 2 plus 3, which is 5. And sine of 0 is 0. So I'll get negative 1. Now I'm going to go ahead and graph these as I get them this time. And you can go ahead and graph them also. So make it a fairly decent grid with somewhat even points there. So first thing I'm going to graph is 5, negative 1. And I'm going to put a point. And then again, I don't really know if that's for sure the starting point, but that's where I've started. Okay? And then let's go to the next point. Well, pi over 6 or pi over 3 or pi over 4, those are all things that we know, but they may not give me the best values. I'm going to pick all the quadrantial angles, which will be the quadrants. So I'm going to pick pi over 2, pi, 3 pi over 2. And then if I had to, I could put more values in the middle, but I don't want to get square roots of 2 in there and stuff like that. That'll be hard to graph. So I'm going to go ahead and go with the nice angles. So if I do pi over 2, cosine of pi over 2 is 0, so 2 plus 0 is 2. And sine of pi over 2 is 1, so negative 1 plus 2 is 1. So I will have a point at 2, 1. And I'm going this way. So I'm going to make a guess. It's a curve, so we're going to say we're going like this. And then I'm going to put an arrow. I know I'm going that way. All right, so let's pick the next one. So next one that's on a quadrant would be pi. So if we pick pi, if we plug in, cosine of pi is negative 1. 2 minus 3 then is negative 1. Sine of pi is 0, so we get negative 1. So now we have the point negative 1, negative 1. So we seem to be coming around here like this. We can put an arrow there. And then let's go to 3 pi over 2. 3 pi over 2 is going to give me 2 and negative 3. You can practice plugging those in, and you should. But I'm going to go ahead and go a little quicker here. So 2 negative 3 would be right here. So we're going to, come around here to this point. So arrow this way. And you should be able to start to see what you think is going to happen here. So let's pick 2 pi. If you plug in 2 pi, you're going to get 5 negative 1, which is right back where I started. And so we came around full circle. So what does this shape, that's really bad, my orientation is really off here. So do you remember, you should remember this shape from Algebra 2. And this was one of the conic sections, and this appears to be an ellipse. So let's review some things about an ellipse and see if we could figure out what this equation might be without eliminating the parameter, and then we'll eliminate the parameter and see what it looks like. So it looks like the center is right here. It appears that the center of this thing is here at 2, negative 1. And then remember on an ellipse you had an axis that ran through this way, that was called the major axis, and then you had the minor axis that ran this way. And this distance right here was an important number. That distance is 3, and this one was 2, and it had to do with where they went into the equation. So your equation for an ellipse is x minus h, where h is your center, squared over, well, in this case, a squared because the length is in the x direction, plus y minus k squared over b squared equals 1. A and b are those two numbers, that 2 and that 3, and h and k are the center. So it appears that our equation is x minus 2, whole thing squared, over a squared, a is the 3 there, so that would be 9, plus y minus negative 1, because my center here appears to be at 2, negative 1. So it would be y minus negative 1, which would be y plus 1 squared, all over b squared, which would be 4, and that would equal 1. So let's go ahead and go through the process and eliminate the parameter and see if we're right, because that's the equation when you did an ellipse. So we have, let me rewrite those down here where we can see them. So I have 2. So I have x equals 2 plus 3 cosine t, and y equals negative 1 plus 2 sine t. Now if I look at that, this is not going to be like before, where you're going to be able to just solve this for t, because you've got a cosine in there and a sine, and you get a cosine inverse and stuff, and that's kind of a mess. And the main thing is that we can get it into something that we can translate. And so what we're going to do here is we're going to actually solve this for cosine t and solve it for sine t. So I'm going to solve this first one for cosine of t, which means I'll have x minus 2 equals 3 cosine t. So x minus 2 over 3 equals cosine of t. And then this one, same idea. Let's go a little faster. I would add 1 and divide by 2, and that would equal sine t. Now, why was that helpful? Well, we should be able to figure out, we've got a trig function here. If we remember our Pythagorean identity, we know that cosine squared plus sine squared equals 1. So instead of cosine squared, I can write x minus 2 over 3 squared plus y plus 1 over 2 squared, and that equals 1. And so I've eliminated the parameter. There's only x's and y's now, and if I simplify it a little bit, you'll see that we do in fact get exactly what we just wrote if I just square out the bottom term. So that is exactly the same. This whole expression is exactly the same as what we wrote right here. And so we did it by eliminating the parameter. So this in fact is an ellipse, and if you were to graph it, it basically just keeps going round and round and round and round and round and round. Okay, so you can certainly graph that on the calculator and look and see what you get, and I would strongly suggest that you do that, and then actually do some things like change sine and cosine around, but leave everything else the same, and see what happens. See what happens to the graph and how it changes. So that's our beginning introduction to our parametric equations. And so next time on the next video, we'll talk about how that applies to calculus and how we do calculus with it.